It's great. So let's get started. So welcome back, everyone. We're going to be talking about Bayesian inference today. This will be kind of just reaching the surface of Bayesian inference. We're not really going to go very deep. There are whole classes on this, including here at the U. But I'm going to introduce you to the idea and kind of open up a little bit the power of Bayes' rule that we talked about in the last lecture and show you a little bit how not going beyond just the likelihood, what we can do with that. And this will help frame the sort of equations we're going to see the rest of the semester. Okay, so we're going to do a little bit more, probably even less than last lecture, derivations with a few equations to get to some stuff that will then look familiar the rest of the semester. That's kind of the goal of this lecture here. Before we get to that, all right, so where are we in the schedule? Okay, we're the last part of the probability review kind of chapter. Probably this part is a little bit less review, probably those mostly the first two kind of lectures here. We have quiz 1 today. Okay, so you all took a practice quiz 0 in the second lecture of the semester. Quiz 1 will be today, right? There's just so you're not surprised about that. It'll be the end of the lecture period. I plan to give between 20 and 30 minutes. So I might stop as early as 3:50, but definitely by 4 o'clock to start the quiz. I expect on average it will take about 10 minutes per student. That's what we're aiming for. So nothing too long. If you've been following along and understanding stuff in class, asking questions when you have them, you probably should be fine. Okay, you are permitted one sheet of paper, one side to use as notes, but nothing else. So everything else will have to go under the desk when you take them. We're going to start enforcing this carefully today. You won't need calculators. There'll be numbers on there, but the calculations will be so simple that calculators will probably not be helpful. That's the plan for the whole semester on these. So on the quizzes. And so if you haven't prepared that one sheet of paper, maybe do it during class, okay? But this is a good way to study and think through what's important here. It may contain stuff from this lecture. If that's not the case, I'll try and give you a heads up. But sorry, next lecture will appear on the next quiz. All right. Okay, if you, yeah, so so some people have different accommodations for quizzes. If that was you, these things may not have gone set up quite right with how the CDA works. So if that's an issue, when the quiz starts, come talk to me and we'll find arrangements for this time and in the future. It was a little bit more complicated than I thought it would be this semester. Okay. And then how many people have looked at the homework so far? Opened the homework. Okay. How many people have started writing down some of the answers? Okay. Okay. So that's okay. You should be able to start on that. You don't, after this lecture, I think you're good to go on the homework, right? So you don't need to delay that. Probably if you had started and at least looked at it, that may have helped a little bit with the quiz. These are not going to be perfectly aligned with each other. They overlap and they're not exactly the same material, but kind of looking at it and make sure you understand all the questions is probably a good idea to do before the quiz that's coming up on similar topics. All right. Okay. So again, we'll see how the homework goes. I'm hoping again it's pretty not too challenging, but we're going to have them every other week. So kind of get into the kind of the cadence of the homework. All right. Any questions on the schedule? All right. Great. Okay, so talking about Bayesian inference. Let's start by just recall. Recall Bayes' rule, and that is the probability of a model given data, or of an event M given knowledge of event D, because we observe data, we know what the data is, we want to find the probability, a score for a model. We can write the probability of the data given the model. And this one is nice because we can compute it. The probability of the model, this is sometimes is given to us, divided by the probability of the data, right? So this is Bayes' rule, okay? And just recall, this one we liked because we can compute. This one was called the likelihood. This one is often given. This one is often given, and it's going to be called the prior. And this one at the bottom, we will often ignore. Okay, and we talked about that one. We'll often, because we're given the data, we don't need to know the probability of it. We kind of factor this out, okay? And we talked through last lecture, we talked through two examples. The first one was the cracked windshield example. Okay, so in this one, we had discrete space of the models, right? So the sample space of the models we could choose from, there are only three options, A, B, and C, and then we just computed it for each of the models. That's what we did there, and we're able to factor in the prior, okay? Then we talked about the other example, which had to do with, forget if we even, we motivate, this was maybe about the height, okay? And in the height, we had a continuous space of the models. Okay, but we only L in there, or N, and only looked at the likelihood, no prior. Okay, and we said that if we have if this likelihood, if this was a normal distribution, right? We had this normal distribution, which was the right? It has a value mu and sigma, and this was 1 over 2 pi square roots sigma x minus the distance between some value x and mu squared divided by sigma squared. I saw that this equation is right outside this room. So when you're walking in the room on the white wall with white letters, so it's kind of hard to see white on white, but this equation is right outside this room. This is the normal equation. If you assume normal noise, then we could simplify this model so we could solve it even though we had a discrete continuous space of models. We said, well, if you had a bunch of data you observed, we went through some equations. We're going to kind of review this a bit today, but we're able to solve it because we picked this nice equation. Okay, and so this allowed us to do this, but we didn't yet use a prior. So we're going to go back and look today at continuous model space, but also having a prior, and figure out a nice way where this fits together and the equations simplify again. Okay, and then this will be a guidance for the rest of the semester. These are equations we should expect to see. Yes? No prior. Prior, remember this guy is the prior, this probability of the model. And when we talked about this height example, we'll go through a longer height example today. When we looked at it, we didn't assume a prior. We just assumed we had some measurements with normal noise on the measurements, and we'd want to kind of understand the most likely model. So we only looked at that purple highlighted equation up there, the probability of the data given the model, and that was something we could explicitly calculate. Okay, we'll do that again, but we also want to incorporate a prior as well here. Okay, and we'll be a little bit more careful with the notion of continuous random variables as well today. We kind of were a little bit fast and loose with that. I wrote probability a bunch up there, and we won't have to write it in terms of PDF, so I'll try and write down some mathematics that looks like the PDFs, but it should look familiar to what you saw the last lecture. So hopefully not so bad, even though there's going to be a bunch of equations and things that it's a little bit hard to kind of, the equations don't map to the English language quite as conveniently as when you're talking about discrete probability. And so it's a little bit hard to kind of speak out what we're saying, but we'll go through the exercise of the mathematics, and so that will be the goal of the lecture today. Okay, great. So what we'd like to do is, so I'm going to kind of, let me start back with probability again. We're going to look at the probability of the model given the data. And we want to transform this into the probability of the data given the model times the probability of the model, right? We have these different kind of terms here, and we wanted to transform from the left. We want to understand which model is most likely, and that's what, given the data we've observed, that's what this is saying. Which model is most likely given data observed. Okay, but in order to actually calculate this, we could say, what's the probability of seeing a particular data point given the model? That's an equation we can write down. And that is what this equation was telling us, right? So this we could calculate, and then we're also going to be given this prior, okay? And then there was this other term below that divided by the probability of the data I wanted to ignore because we didn't really know how to calculate that by itself. Okay, so what we're going to introduce now is this symbol. Okay, it looks kind of like a fish or something. And this means proportional to. Okay, it means proportional to. And let me write down an equation, and then I will I'll say this means that if, let me not use F, if H of X is prop 2, C times G of X, if H of X equals C times G of X for all X, for some constant C. I don't have to know what the constant is, but there exists some constant for which this is true. Okay, question. So is that it's different from the Greek letter alpha, yes. One thing computer scientists did, this was, they invented LaTeX, and LaTeX is the language which we write down all of mathematics in. That's what you would use in overleaf, and they invented a bunch of different symbols that are beyond the Greek thing. So this in LaTeX is prop 2, okay? It's quite possible, and I don't know the history of all symbols, so it's quite possible this started by some mathematician writing down some alpha or some other symbol or what it meant. That it's now encoded as prop 2 in LaTeX. That's what that symbol is. That's the most the precise definition of what that symbol is, prop 2. But it's kind of like an alpha. It's kind of like an infinity with the side chopped off. It's a little different than both. If you look in the textbook, you'll see one way of rendering it, but there are different fonts and they render symbols differently, just like other fonts do. So, but this is a, yeah, prop 2. Yeah.
Big X. So HX. The sign C and G is that big X?
Yeah, so these are for some argument of the function. These are just abstract functions H and G.
Oh,
right? So these are for there's some abstract function H of H, and it's proportional to function G.
Oh,
right? If for all arguments X of those two functions, I can multiply C by this. I don't need to know what C is. That's the powerful thing of the prop 2. I don't need to write down what that C is. I don't need to know what it is. That gets brushed under the rug, right? And this is useful because we just want to find the argument which maximizes that function, the argmax, right? And I don't care about this constant in the argmax. Okay. Yeah. Likely given data observed. That's kind of the principle we want to do. That's not exactly what that equation is doing, but that's what we want to do with that equation. Also, given the prior knowledge that we have, there's lots of words here, but like I want you to remember that's kind of what we're after here. Right, yeah.
so
That's right. In this case, it's 1 over the probability of the data. That's correct, right? In other cases, it could be something else. And as we transform, we do some algebra, we'll see that when I have another absolute constant, like 1 over square root of 2 pi, I can just throw that into the prop 2 and ignore it. So it's kind of like the big O notation. It allows me to really simplify the sort of equations I need to write to get to the answer I want. But now we get to do it in code too, because anytime there's a constant multiplier and we're optimizing something, we can just drop it because it'll give us the same optimum. Yeah.
So if h of x equals 2 of x, what does it say after that?
For some constant C. For some constant. Thank you. Yeah. Just my. Yeah, I have trouble talking and writing at the same time. So if you can't read it, please stop and tell me. Okay, great. Okay, so we want to write this, but this is for discrete things. This is useful when we're going to be writing it with PDFs. So now we want to do a continuous version. Okay, so now we're going to say that first we're going to map down. We're going to say f of d given m. Okay, we're going to use f for this. This one is going to be called the likelihood. Okay, whenever I'm looking at the probability or the PDF, in fact, the PDF of the data given the model, this is a probability density function now where I can input the space of the data. It's a little complicated. I have n data points. Each data point might be a real value. So I have n parameters and arguments in here. And the model is given. But this is a PDF function. We'll write down what these are. This will be a continuous function times the prior. The prior we will write as pi of m. It's a different function. Okay, so we usually use lowercase letters or Greek letters to describe these functions. It's a little confusing, but this kind of aligns with the notations you're going to see in papers. So I'm just trying to talk you through it. Okay, and this will be proportional to the posterior. The posterior will be a function m given d. This will be the posterior. Okay, so now I'm trying to use notation that we used 2 lectures ago when we talked about probability review for continuous random variables. Now we have these functions that have a range of the function which is continuous, right? We have now the continuous space of models. This is going to need to be filled by parameters. Okay, so actually what we want to do is I'm going to replace this uppercase m by a lowercase m here, because we're going to look at a single parameter value of the model, or a single scalar value. In this case, we'll think of like the height of people again. Okay, and so this will be kind of the average height of people we want to try and understand. The data, I'm still right as a capital letter here. It's going to be a set, and we'll tend to use capital letters for sets here. Okay, we'll turn this into smaller functions so that the argument is always a single scalar value. Right? We can remember when, when D equals x1, x2 up to xn, a set of observations, and each xi is from some unknown distribution. Let's call this psi. I don't know, but these are IID. These are independent observations. We'll get back to this notation again. They're independent. Then we can write f of D given m, remember, as the product. I'm off the bottom again, aren't I? Okay, as the product, right? Product of I'll write it and then I'll slide it up a little bit, of G of xi. Okay, let me move this. Okay. Okay, so we'll be able to write this with m here. Okay, so we're going to assume that our data is independent observations. That means that we can write the likelihood of the whole data set as the product of the likelihoods of the individual data points, and this will be an equation we can write down explicitly. Okay, it'll take in some guess of the model, and we'll be able to write down this equation exactly, and because they're independent, we can factor it out as this product. Okay. Okay, so yeah. There's some distribution. This is an unknown distribution. And I've written a psi to represent it. It does not matter as long as we know the xi are independent. Okay, the key thing is that they're independent of each other. And next lecture, we'll start talking about this sort of thinking, what that means. I don't want to get into it, but we just need that these xi are independent. Then I can factor this up here. Okay, so now I've written these each as functions. These are all going to be kind of continuous functions. So we're going to go through an example where this will make sense. And in fact, most of data analysis will use very similar variants of the same equation. So I'm going to write it abstractly because this is the general formula, the big principle that everything will use. And then we're going to see equations, and we'll go through calculations. And once we've derived a simplified form, that form will stick, and we'll see that the rest of the semester. Okay, so I just kind of want to go through the math so you know what it is, and you understand where the equations will get to by the end of this lecture are I'm trying to come from. Okay. Okay, so let's start with the prior. Okay, we're going to talk about our prior. This was effectively you can think of as the probability, but it's a PDF of the model. Okay, and so we're going to talk about an example where we gather the height of a bunch of people, but we want to say, I have a prior knowledge that I think the average height of a person is about 66 inches. Okay, so I think this is roughly 66 inches. Okay, I think the average height of a person is roughly 66 inches. This is like 5'6". So let's say this is about right, but I'm not sure about it. So I'm going to say roughly plus or minus 6 inches. Okay, I think the average height of a person, or maybe a subpopulation, let's say we want to look at the average height of someone at the University of Utah. Okay, on average, maybe people are about 66 inches. Maybe at the University of Utah, they're slightly taller, slightly shorter. I'm not sure. I'm not sure what at the University of Utah will be. Maybe there are a bunch of basketball players here, and so the height is taller. So plus or minus 6 inches. Okay, and so I kind of want to turn this into an equation, right? I want to turn this into a continuous equation that captures my guess of what this height is, right? So I want to think there's the space of the height, and this will be, and I think on average, roughly, there'll be 66 inches, and I'm going to say plus or minus, say 6 inches, right? So it's probably between 60 inches and 72 inches, right? So that's kind of the range I'm thinking in. And I want to turn this into a continuous equation. So what are we going to do? If kind of in doubt about this, you kind of want to use the normal distribution, okay? And just drawing a picture, kind of a uniform distribution between 60 and 72 might look a little bit simpler, but if you wait a little bit, the normal distribution will be simpler. So that looks like a curve that looks like this. Okay, this is kind of like a normal distribution. Often I try and do like a script n, okay? And this will have parameters mu equals 66 and sigma equals 6. Okay, so I'll say that this distribution is roughly a normal distribution. And this, again, so that implies we're going to set our distribution. So we're going to say that pi of m is going to be equal to this. So if we say that this is equal to the normal distribution 66 and 6. Oh, that looks a little devious, but okay. This will be 1 over 2 pi sigma squared. Squared, if you put it under the square root, e to the power, that's what the exp stands for, negative the difference from mu. This is my mu is 66 in this example, minus m, that's my parameter, right? M is the argument of this, squared divided by sigma squared, right? Okay, so if you're wondering where this m came from, that's the value, that's the distribution. So now if I drew a random sample from the distribution, I'm more likely to pick something here and less likely to pick it further out, right? This is what the distribution is saying. But every possible height is possible. I haven't ruled out any heights. Probably want to rule out being less than 0, but we're not going to worry about that sort of stuff today. You could do a beta distribution. We're going to ignore it. The calculations would be much more complicated. Okay. So we're going to use this equation written outside the room, the normal equation, to model our prior guess of the average height of a University of Utah student. Okay, this is our guess of the average height of U of U student. Right? Okay, who thinks this is a good prior? Is this a good guess? What is seems kind of reasonable? What could go wrong with it? It has to be greater than 0. This has some probability of being less than 0. That'd be pretty weird. Heights of students is actually pretty bimodal. There tends to be actually fairly normal distribution of students as long as you choose either kind of male or so female students. They both have kind of normal distributions of their heights, but they are not the same mean. So it's probably bimodal, and but the average of two normals is again going to look like a normal distribution again. So we'll kind of see next lecture. So this is probably okay if I combine them together. It's okay. This depends. We can decide how much importance to put on this, but for now, we're going to say this is our starting point. Okay, so this will be our prior. Gives us a continuous space, our best guess of the average height of University of Utah students. Okay, so now we want to do data plus prior, right? So the prior was this model here, which we said was the normal with a mean of 66 and a standard deviation of 6. Let's say last time we just looked at the likelihood and we got the maximum likelihood estimator, the MLE, and we decided that if data was a set of values in real values and there was normal noise, okay, we'll come back to this, then the MLE which was the argmax of the choice of the models of this, was going to be 1 over n I equals 1 to n of xi. It was the average of all of the values we saw. Seems pretty intuitive, so that's good. If it matches your intuition, you're probably on the right track. Okay, so let's say that we got this and it equaled 5.5. Okay. Okay, so we have this. We said this was our prior, and then we got back the maximum likelihood estimate, and it was 5.5. What probably happened here? Is this good? What should before we do any sort of combining of continuous probability density functions and equations, we should look at this and kind of think through it a little bit.
So just to make sure what I understand, this is that after taking the heights of everybody.
Yeah, I took a bunch of heights. Yeah, so I said 5.5. I didn't say inches. Right? I told you before that this one was measured in inches. Okay, and I got 5.5 here. And I just look at numbers, right? You run it through your Python script and out comes the number 5.5. And you're like, oh boy. That if I look back at this distribution, 5.5 is way off here. It's way in the tail. It's exponentially small, that number here. In fact, it's squared exponentially small. So it's going to be a really, really tiny value under my prior. What is going on here? Yeah, and back. Feet, yes, probably what happened is that this was probably in feet instead of inches, and I probably got the units wrong here. If your data and your prior are way off, it's good to kind of do a sanity check and see what's going on here. Do they kind of match? Before I do anything, sort of work through the, the full posterior calculation, I should just check, do they match at all? And if they don't match, there's probably some simple, silly mistake I made. And it's often mismatch of units. This is a very common sort of mistake to me. You'll probably make this mistake in your careers where you combine two things in different units, and you kind of want to keep checking these things and see if they match up and say, this was probably feet and that was probably inches. And if I multiply 5.5 by 12, I get back 66, right? So I can say, this was actually 66 inches. And then I'm like, great. So probably the right answer is probably about 66. The kind of the most likely value of my prior and my some likely estimate, they match exactly. I should just stop here. Let's just say 66 inches is my best guess, and I can stop probably. Okay, but they won't exactly match. But if it was 5.4, then we have to say, okay, how do we combine these two things together? Okay, great. Okay, so now we want to simulate. We actually did this. So I actually did some measurements. So now I have my prior of the model was going to be my normal distribution, right? And now I'm going to observe my data d x1, x2, ... n. These are going to assume to be independent. And I want to build my maximum likelihood. I want to build my likelihood. I want to calculate this function of probability of the data given my model, right? This likelihood, this continuous PDF. And because I'm going to write this as the product of some function g of xi given the value m. And I can do this conversion again because they're independent, then I can factor this out as a product. Okay, so I can write this down, and now I need to say, okay, what is the likelihood for a given choice of the model, 66 inches or 65 inches? What's the likelihood I saw a particular data point? These are actual observations. This might be 68 inches. This might be 72. This might be 63 inches, right? I get a bunch of these actual values in here. And when I calculate this with the formula, what we're going to do, we're going to again use the normal distribution. Okay, I'm going to say now, because it's a nice equation and because it's on the wall behind this room, we're going to say that this is equal to the normal distribution with the, what is the mean of the normal distribution going to be? Well, the mean will be my choice of the model. And now I need to choose how spread out it will be. Let's say I have to measure with the precision I measure with. And let's say that this precision, the standard deviation is 2 now, right? Maybe the height of the shoes gives me some off, or are they wearing a hat or their hair, or my measurement's not very bad. Let's just say that our measurement error here is 2. Okay, right? This is, we're just going to say that for this example. Okay, we choose something before, it didn't matter what I chose, I got the same answer, but now this will matter, it will matter what choice we make here, and we'll kind of walk through how this plays a role here. Okay, so now we have the setup. We have a prior for the height was about 66 with 6 inches deviation, And then we have observed some data and we put another normal distribution on here. And now we can write down this posterior, right? The posterior, which was P of the effectively the probability, but the probability density function of the model given the data, right? This is what we would like to calculate. And we're going to use a proportional to, because we don't want to worry about those other terms. We'll use proportional to. This will be proportional to the PDF of the data given the model times the prior. Okay, we have equations for all these things. In fact, we can write this as proportional to the product 1 to n of G of, I put that, of G of xi given the model, and this whole thing times the prior. Okay, so this will be our equation. The next slide, I'm going to kind of write out things, and we're going to see that again, because of our nice choices and by the extra use of the prop to, the proportional to, we'll be able to kind of simplify these equations. Won't be so bad. Again, they start out looking like this normal distribution, but then I promise you, we'll use the log likelihood and the log prior, and things will kind of are going to simplify. Okay. All right. So let's actually directly write out the natural log. This is an ln, that's a log base e of the posterior of the model given the data. Okay. Yeah, okay. This will work well. This will be, I'm going to say, is going to be, well, so the log is not something you pass through something proportional. So actually, I'm going to write the log of the so what's the log of the posterior will be proportional to the log of the product G of xi given the model times the prior of the model plus a constant. Okay, so when I pass through a log, I have to, there's the constant factor that I was dealing with in the proportional to before I did the log, that turns out to be a constant factor. So now I need to say there's some constant that I'm not going to worry about here. Okay, so now I can start simplifying things. This will be proportional to the sum of I equals 1 to n of the natural log of G of xi given m, right? So I can turn the product into a sum by passing it through the log, plus this the log of the prior, okay, plus some constant here. Okay, again, I'm going to end up maximizing this, so I don't care what the constant is. It's an absolute constant. Okay, and now this will be proportional to, and now I take the log, inside the sum, I take the log of the exponential, okay, and that log of the normal distribution, right? That was the product of the coefficient and the exponential. So this itself is going to be a negative xi minus m squared divided by sigma squared. This was, what did I say? This was 2 squared, right? Plus the natural log of 1 over square root 2 pi plus times 2 squared, right? So there was this coefficient in front here. Okay, and this was also plus, and then the prior becomes, this will be instead 66 minus m squared, and now it's going to be divided by 6 squared on the bottom. Okay, and then there's also the coefficient also goes inside the log, but that's also a constant. So I'm just going to throw that into here. Okay, in fact, all of this term can get thrown into this constant here, right? Okay, so this term had no dependence on the choice of m, so it can get thrown into the constant. When I'm maximizing this, I don't care about this value. This should actually be a minus here, right? It was a negative. Okay. Okay, so I did a bunch of steps here. I simplified a bunch of stuff. If you remember, I didn't want to write up those whole equations again, but because I'm taking the log of those equations and I only care about proportional to up to an additive constant, it's really simplified. And now I have these sum of squared terms here. Okay, so let me write this a little bit more cleanly now. There's the minus sign. Okay, and I'm going to have let me just write it this way. I equals 1 to n of xi minus m squared plus this term 66 minus m squared. And I have to worry about those things I divided through by. What I'm going to turn this into is a 1 over 9 plus some constant c. Okay. So how did I get this 1 divided by 9? How did I get that? Where did that come from? Yeah? Yes, 4 over, so this one is 4, this term is divided by 4, this term is divided by 36. But then why didn't I write 1/4 here and 1 over 36 here? Yeah, to simplify it, because I could multiply the whole thing by 4, and it's proportional to, so I don't care. Right? If I multiply by constant factors, 4 in this case, it's the proportional to eats that. Okay, I still need to care about this one has a 1 over 9 in front, and this one doesn't. There's still the ratio of how much they weigh. Okay. Okay, so now I kind of, and when I want to find the argmax of this, right? So this is basically my answer. I want to find now goal, the map estimate, right? The maximum a posterior. Remember, this was the log posterior. So the log posterior, and I would find the goal, the maximum m a posterior, called the map estimate, maximizing the choice of model over this. It's the same as maximizing the log of this because it's a monotonic function, is equivalent to the arg min of sum I equals 1 to n x minus m squared plus 1/9 66 minus m squared. Okay, so this is before we could just take the average to solve for this quantity. I've gotten rid of the minus sign. I've turned the max into a min. Okay, and now I needed to take the minimum of this sum of squared errors. And I have another term here, but this one is weighted differently. What should I think about this? How should I solve this? I want to find the minimum of this equation for m, right? Arg min of m, the sample space, right? I'm going to call this m star. right? How would I solve? Do we know how to solve for this? Is there a simple solution like there was when there was just the sum of the square differences? What if instead of this, instead of this, I did, maybe it's more clear if I write a 9 in front here. What if I put the 9 in front of this guy? What? So I can't, that's fine. It's the same minimum. I just multiplied the whole equation by 9, right? So this term gets up by 9, this one goes up by 9, and this cancels out to a 1. Okay, this is equivalent. Okay. This is kind of like if I had 9 copies of every data point. If I had 9 copies of every data point, and then I averaged in one data point worth that was at value 66. 66 is like one of the other observations. Okay, so it's kind of like 9 copies, and then I can take the average. I have to care about everything, but this tells me how important is this versus this. Okay, so we're going to go through one more thought experiment in the next slide, and we'll wrap up and do the quiz. Okay, but like this, I can do this as there are 2 ways. I can do this. One way I can do what's called a weighted average. Okay, which I'm not going to work through because we're kind of almost out of time. But the calculations are pretty simple. I just kind of add weights before I divide by the total number. I just change I have a weighted sum, and then I divide by 9 times n plus 1 things instead. The other one is I can make 9 copies of each data xi, right? So I can just make 9 copies of each of the data points, and then I can take an average. Once I have 9 copies, I can just use my same algorithm to take an average of them as before, and it will give me the right answer. Okay, so when I get sum of squared errors, they're often really nice algorithms to solve the minimum explicitly. Sometimes we'll use this later in class to get really cute algorithms. Sometimes we'll have to use gradient descent. Okay, but here we get a really nice algorithm, how to do it to calculate it specifically. Take the average and back. Yeah, so we would use this if we collect a bunch of observations of heights. And we also have a prior distribution of what we think the heights are. And which would be the distribution that we come in our best guess of what we think it is. If it's too far off from that best guess, something's probably off, like the units are wrong. That's one use of it. The second is it slightly changes the solution a little bit. I get a little bit of weight on this data point. Okay. In this case, the weight of the prior in the solution is really small. Let's say I have 100 observations and I weight them by 9. I had like 900 of these then, 900 values here for 1 prior. So it's like 1 out of 900 of my total estimate. In this, what we've done here, the next slide will change it a bit. In this case, it has a very, very small effect on the answer. But if we change how we set up the prior, it can have a much larger effect. And we may want to do that in cases where we don't trust our data, or in cases where we want to rule out certain things.
So you want to wait.
I might want to rule out it being negative, or I want to rule it out in case I don't trust my observations. The observations are kind of like something came in really weird. I'm like, let me revert back to my prior.
So that
It's kind of like scaling, yeah. but it's scaling is not the right technical term here. It's kind of pulling towards an estimate that we come in with, right? We started with this picture right here, right? And then we made a bunch of observations around here. And these observations allowed us to get a better estimate. But if these purple dots had all been over here, we might be like, this is a little weird. Let me pull the estimate back this way. Okay, and this shows up, this sort of equation that we see here will show up in all of data analysis. And this term can take some other forms, but we'll have all the estimates from our data, and then some other term that we say, we want the solution to kind of look like this. So we're going to kind of use this as our baseline and kind of bias our data towards this solution a little bit. So we'll see this form will show up in all of machine learning. This is sometimes it's called a regularization term, where you regularize your data, your solution to be more like something you want it to be, maybe sparse or some other stuff. Yeah. I drew that arrow first. That arrow's not needed there. Yeah. Okay. This is the goal of the map estimate is to do this. Okay. Let me very, very quickly say, what if we change the prior to be 66, but where sigma equals 0.01. Okay, what if we made the prior distribution say, I really trust the national average of the height of people. I looked up, and the national height of someone did a big survey of 100 million people and measured their heights, and the average was exactly 66 inches, and I trust it a lot. I don't think Utah deviates from that very much. So I want to say my standard deviation of that is actually going to be quite small. What will happen is that this term, okay, and it will be an exercise for your at home or to look up in the book. Okay, now my map estimate will be M star is going to be the arg min of M of one of the data here plus 66 minus M squared, but this term will now be weighted something like 400 instead, right? So I'm gonna, if you work through the calculations, the effect of decreasing the variance of my prior, so my prior is much narrower, is going to increase the weight of this term that I give to this value of 66. You're going to have to really have a lot of data to convince me to deviate from that. So if you change that distribution, it changes the weight of this one term you've added. And so now instead of being worth 1/9 of a point, that prior estimate is worth 400 data points. You'd have to show me way more than 400 data points to convince me to move too far from that. That's what that's saying. So by changing these values in the prior or the weight, this is a valid thing to do. It's telling you how much confidence should I put on my prior versus on the data I observe. And there's going to be this trade-off. Okay. Great. Okay. So we'll stop here for the lecture, and we're going to do the quiz. Question? I think we might